Good morning, students. Today's topic is bright field microscopy and dark field microscopy. We will begin with bright field microscopy. The fascinating world of microorganisms would have remained unknown had the microscope not been invented. History of microscope. Roger Bacon described a lens for the first time. However, his observations were not pursued immediately. Thereafter, in 1950, Hans and Gregorius Jensen constructed a crude type of operational microscope which is 10 to 30 times magnifying the object by placing two lenses together, which permitted them to see minute objects. In 1609 to 10, Galileo Galilei made the first simple microscope with a focusing device called oscilla and observed the water free through his microscope. In 1617 to 19, the first double lens microscope with a single convex objective and ocular appeared, the inventor of which was thought to be the physician Drebbel. Here you can see the pictures of Roger Bacon and Gregorius Janssen. C. Drebbel in 1617 has developed the first double lens microscope. This microscope was used to study the cells, plants, and animal tissues, and also the minute living organisms. Until then, the name microscope has not been given to this device. The name microscope was first proposed by Faber in 1625. You can see the picture of the Giovanni Faber. The credit of developing a compound microscope with multiple lenses goes to Robert Hooke, 1665 of England. It was only after 1670 that a cloth merchant of Delft, Holland, Antony van Leeuwenhoek, who lived from 1632 to 1723, started his hobby of making microscopes, and in 1674 he discovered the fascinating microbial world through his microscope, which gave 50 to 300 times magnification. Considerable progress was made in improving the microscope in 19th century. The introduction of oil immersion by MEC in 1869, substage condenser by Abe in 1872, epochromatic objectives with suitable eyepiece by Abe and Jesse in 1886 were landmarks in the improvement of compound microscope in the 19th century. Here you can see the picture of a microscope developed by Anton van Leeuwenhoek, and some of his drawings represented as figure A, B, C, E, F, G, etc., showing the drawings of some bacteria of that time. Jeronic in 1932 has developed phase contrast microscope. Electron microscope was invented by Knoll and Rusko in 1932. It was a transmission electron microscope. Knoll demonstrated the feasibility of scanning electron microscope in 1935. 3 years later, a prototype instrument was built by von Ardin. Siemens has produced the first commercial transmission electron microscope in 1939. Kunz developed fluorescent microscope in 1945. Interference contrast microscope was developed by Merton and co-workers in 1947. While studying microscope, we like to know the different types of organisms and their sizes, and which can be used with an unaided eye and with microscope. With unaided eye, we can see a size ranging from 10 meters to 100 micrometers. While using light microscope, we can see 1 mm to 100 nanometers. And while using electron microscope, we can see even the size of the atom, which is of 0.1 nanometers to 100 micrometers. Understanding microscope requires knowing about length and bending of light. Light is refracted or bent when passing from one medium to another. This refracted light is measured by refractive index. Refractive index is defined as a measure of how greatly a substance slows the velocity of light. Direction and magnitude of bending is determined by the refractive indices of the two media forming the interface. Focused light rays at a specific point is called focal point. The distance between the center of the lens and the focal point is known as focal length. Strength of the lens relates to focal length. Shorter the focal length, more magnification. Here in the picture we can see a lens through which light is being passed and forming a focal point named as capital F, and this distance between the center of the lens and the focal point is represented by small f known as focal length. Light microscopes. Light microscopes are of many types like bright field microscope, dark field microscope, phase contrast microscope, fluorescence microscope. All these microscopes are of compound microscopes, which means the image is formed by the action of more than two lenses. Bright field microscope. A compound microscope is the primary tool in microbiology. Therefore, a clear understanding of the structure, use, and manipulations of a compound microscope is a must for all the students of microbiology. Bright field microscope produces a dark image against a brighter background, has several objective lenses. Parafocal microscopes remain in focus when objectives are changed. The total magnification is nothing but the product of the magnifications of the ocular lens and the objective lens. Let's get familiarized with the parts of the microscope. First, it begins with an ocular or eyepiece, followed by the body. Below body, we can see a nose piece, which bears four objective lenses. Then it is followed by a mechanical stage. Below the mechanical stage, we can see a substage condenser, and below this condenser, we can see an aperture diaphragm control. Then base with light source, then field diaphragm lever, followed by light intensity controller. On the other hand, we can see the arm of the microscope, and below this we can see the coarse focus adjustment knob, which consists of a fine focus adjustment knob followed by a stage adjustment knob. Lenses. Eyepiece are of different types. It is an essential part of the microscope. These eyepieces have different magnifications ranging from 5 to 20 times. It has field lens towards the object and eye lens closer to the observer's eye. The objectives are generally with three different magnifications. Low power is represented as 10x, high power as 40 to 45x, and oil immersion as 100x. The focal length of these lenses are 16 mm, 4 mm, and 1.8 to 2 mm respectively. These objectives are mounted on a revolving nosepiece for convenience. The eyepiece and objectives are fitted at the two ends of a hollow tube called the body tube or the body of the microscope. The next important part or other parts of the microscopes include adjustment knob, stage, mirror, substage diaphragm, and condenser. First, let's go with adjustment knob. In some microscopes, coarse and fine focusing adjustment knobs are provided in order to lower or raise the body tube with lens for rendering image clear. This is done by rotation of the knobs. The coarse adjustment is meant to bring to object into vision, whereas the fine adjustment is used for focusing finer details. The next part of the microscope is stage. The object is to be observed, is kept on a glass slide and placed on the stage. It may have clips to keep the slide in desired position or a mechanical stage of horizontal movement of the object. In some microscopes, the stage may be raised or lowered with coarse and fine adjustment for focusing the object. The next part of the microscope is mirror. Mirror reflects light which is transmitted through the object. For observing it, the mirror has two planes, one concave and the other plane. When natural light is available, the plane mirror may be used for reflection of the light because concave mirror would form window images. However, with artificial illumination, the concave mirror is necessary for higher magnifications, whereas for lower, the plane mirror may be used. The next part is substage diaphragm. It's meant to control the amount of light transmitted through the object. Substage condenser. It consists of convex lenses which concentrate and intensify the light reflected by the mirror. With objectives of magnification exceeding 10x, the use of condenser becomes necessary for narrowing the cone of transmitted light, which would fill the smaller aperture of the objective. The condensers usually employed are called Abe condensers, and these are used with plane mirrors. Next, magnification. Magnification is defined as degree of enlargement of the image of an object provided by the microscope. It is the product of individual magnifying ability of ocular and objectives. Example for magnification, measurement of magnification is, for example, if the ocular magnification is of 10x and objective is 40x, specimen magnification is up to 400x. There are certain factors which play an important role in magnification, like optical tube length, focal length of the objective lens, magnifying ability of the ocular. So, the total magnification of the objective image can be calculated using the following equation, which is equal to length of the optical tube by focal length of the objective into magnification of ocular. Next important factor in microscopy is resolution power or resolution. Resolution power of a bright field or compound microscope is defined as its ability to distinguish between two particles situated very close. In a magnified image, the object should not only larger but the detail should also be clear. This is possible when a microscope has the ability to see two points situated very close as two distinct entities. In other words, resolution power may be said to be the minimum distance at which two structural entities of an object can be seen as discrete individual structures, even in the magnified image. The wavelength of light used is a major factor in determining the resolution power. Shorter wavelength produces greater resolution. A naked human eye resolution power is around 0.25 millimeters. The resolution power of a microscope can be enhanced by using oil immersion. Here in the picture, you can see how without oil, the light is distracted and producing a longer wavelength. In presence of light, the wavelength is shortened and the resolution power is enhanced in this fashion. There are certain factors which influence the resolution power, like wavelength of the light, numerical aperture. Usually, the wavelength of light is of 400 to 750 nanometers of visible range. Numerical aperture is defined as a property of lens that determines the quantity of light that can enter into it. It depends on refractive index and annular aperture. Refractive index is represented by small n, annular aperture by small f. Thus, the formula for numerical aperture is n sine f. In the same way, the formula for resolution power is equal to wavelength of the light by 2 into numerical aperture. Bright field microscope is used for studying wet mounts, hanging drop method and staining methods. Here we can see the picture of Staphylococcus aureus stained by crystal violet under bright field microscope, and the other side we can see RBC wet mount of an RBC. Bright field microscope overview. Simplest optical microscopy illumination technique. It uses visible light as source of illumination. The shorter the wavelength, the greater the resolution power. Contrast comes from absorbance of light in the sample or from staining. When the diaphragm is wide open, the image is brighter and contrast is low. Next, moving on to dark field microscope. This is a picture of Treponema palladium in a dark field microscope where the field is completely black, illuminating the organism or the object alone. Dark field microscope permits the detection of unstained small biological objects which otherwise provide insufficient contrast. In a dark field microscope, the normal condenser of light microscope is replaced with a dark field condenser that does not permit light to be transmitted directly through the object and thus through the objective lens. The dark field condensers focus light on the specimen at an oblique angle in such a way that light does not impinge on the object and does not enter the objective lens. Thus, only light that reflects off the object is seen, and in the absence of the object, the entire field appears pitch dark. This microscope helps viewing every small bacteria and large viruses, but it is not helpful in distinguishing the internal structure of any bacterium being viewed. This is a picture of dark field microscope. We can see the objective lens, then only scattered light is being transmitted and the direct illumination is blocked. Some light scattered by the sample, it forms a this is the condenser lens below by light source. The light source, we can see it is forming a cone. That is the speciality of this dark field microscope. These are some of the pictures in dark field microscope like paramecium, volvox and spirogera, and the other side we can see Traponium vincenti. Advantages of dark field microscope. It helps in viewing live microorganisms or unstained microorganisms because staining leads to killing of the organism. More detailed view of external features. It adds on adding an fluorescent dye increases the ability to see the specimen. Disadvantages are it's better when the room is completely dark. It needs an intense amount of light from the microscope to work, and it can be easily mistaken dust for an organism. Comparison between bright field and dark field microscope. Light from a plane wave source is focused through an object by a condenser, whereas in dark field an opaque disk is put between the source and the condenser, blocking out the middle of the beam. In bright field microscope, some light is blocked by opaque parts of the object or reflected away at boundaries between compounds or materials of different refractive indices. In dark field, the condenser focuses the beam onto the sample. In bright field microscope, the remainder passes through the objective lens to the observer. In dark field microscope, no light enters the objective directly from the source. Light from the beam is scattered by the sample, some scattered into the objective. The bright field, it produces a bright background with object details appearing darker in the image than their surroundings. The brightness of the brightest part of the image is determined by the source brightness and block size. In dark field, only light scattered by the object enters the objective. This produces a dark background with the sample details appearing brighter than the surroundings. The brightest of the brightest part of the image is determined by the amount of light scattered by the object. In bright field microscope, it results in poorer contrast compared to dark field, as the dark areas are generally gray rather than black. In dark field microscope, this result in superior contrast to bright field, as dark areas may be completely dark, while increasing the brightness of the light source brightens the bright areas. Here we can see the difference between bright field versus dark field images. This is the image of a bright field when sample is removed. An electron beam is being passed through the specimen, and that is how the image is produced, a dark color bright field detector. Whereas in the dark field we can see when the beam is passed, it is tilted in a angle so that it produces a cone like uh, light on the field, resulting in a darker field. Thank you.